Hello guys, in this video I will show you the method of fixed length subnet masking as well as variable length subnet masking. First, let's see what subnet masking means. It means that we use an initial network and divide it into multiple smaller networks. Let's say, for example, we have a network 192.168.0.0/16, which means that we have approximately 65,000 number of assignable IP addresses, and we divide this network into 255 number of /24 networks, each having 255 number of assignable IP addresses. Let's see first the fixed length subnet masking method. Fixed length means that every network receives the same number of hosts. In this case, the network with the highest number of required IP address is considered. For example, let's see a scenario in which we need to create a network for 500 hosts, a network for 310 hosts, a network for 244 hosts, 2 networks for 50 hosts each, and 3 networks for 2 hosts each. In this case, the network with the 500 number of hosts is considered when creating the subnet mask. To illustrate fixed length subnet masking with an example, I have created a scenario which requires variable number of hosts for each network, and I wrote it down here in Notepad to solve it together. So we have the network 192.10.0.0/20, and we need to create these networks with these number of hosts. Okay, so let's see the steps we can follow to create fixed length subnet masking. So the first thing we need to do is write down the initial subnet mask, which is this /20 subnet mask, which means that we need to write down 20 ones and then all zeros. So we have 1, 2, 3, 4, 5, 6, 7, 8 dot 8. This is 16 and 1, 2, 3, 4, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so this is /20 subnet mask. When we look at this subnet mask, we can see that the number of assignable IP addresses which we can give to end devices in the network is 2 to the power of 8 plus 4, which means 12. So we have 2 to the power of 12 number of assignable IP addresses. Okay, so let's see if it will actually be enough for us, or we need to use a network with a lower subnet mask. So for this, first we need to convert these requirements. Okay, sorry for the overlay. So this means that we need to convert these numbers into powers of 2, because we can only create networks which are powers of 2. So 500, for 500 hosts we can use the network 512, the network with 512 hosts, and this way we will waste only 12 number of IP addresses, which we could use in another network, for example. For 310 hosts, we cannot use 256, so we need to use again 512. But for 244 we can use 256, and also as a side note, remember that out of 512 addresses, 2 addresses are reserved for the network and the broadcast address, which means that the actual usable address space means 510 number of devices. Same here, and same here. For 50 hosts, we can use a network with 64 number of devices, aka 62 assignable, and same goes for again the 50 hosts, and here we can use a network with 4 IP addresses because we can use only 2 of them. So once we have these number of addresses, let's give them the appropriate notation. That's interdomain routing notation. So 512 means that we have zeros that add up to 512 number of hosts, which means that 2 to the power of 9 will be 512 if I am not mistaken. So once we have these numbers, let's see if we actually have big enough address space to handle these addresses. In the initial network, we had a /20 subnet mask, which means that we can have 12 number of zeros in the subnet mask, which means that we have 2 to the power of 12 number of assignable IP addresses in the original network address. So let's see, this equals to 4096 number of addresses, actually 4094, and let's see how many we can expect from these requirements. So if we check these numbers, then it is 1000. Yeah, I think it is enough. I think we can say it is enough. Okay, so actually this was step 3. Okay, and this was step 2, 1, and here we had step 2. Okay, so now we can move forward to step 4 and see. Okay, so we need to see the new subnet mask for the highest number of hosts, which we can see is 512, which means that, as you can see, yes indeed, 2 to the power of 9 is 512. So so we need 9 zeros in the subnet mask instead of 12, the original 12. So the new subnet mask then will be 11. As it seems, we have 8 plus 1, 9 zeros, so which means that new subnet mask will be 23. Okay, so we have this, and I think we are finished with step 4. So let's go to step 5. Step 5, the magic number. The magic number is the number which every network increases with. If we go back to our original example, here we can see that every network increases by 1. So the magic number here is 1. But how can we find the magic number? In our example, in the new subnet mask, the position of the first 0 is in the 3rd octet, which means that the last one is at position 2, as we can see from these 2 rows here. So the magic number will be 2. This means that our newly created networks will increase by 2 in the 3rd octet. So therefore we have these networks, for example 192.10.0.0 all the way up to 192.10.1.255/23 as a single network. And then another network starts from 2.0 and another starts from 4.0 and so on. And we also know that these networks all have 512 number of addresses, from which 510 are usable. Okay, now we created some networks, and actually since we use fixed length subnet masking, this means that we created all the networks. And finally, what is left is to assign for all of these networks a usable network address. So for example, for these 500 hosts we can use this network address, and for these 310 hosts network we can use this network address. As you can see, these networks all have the same subnet mask, which means that all have the same number of assignable IP addresses, which means 512 in this case. And this is a problem because, for example, these two host networks all have 510 assignable IP addresses in their network. So it means quite a waste of the address space. And to solve this problem, variable length subnet masking is used. So again, let's see why we do not use this FLSM or fixed length subnet masking. Well, the one reason is because VLSM is used, and again, it wastes the IP address space by requiring more addresses than otherwise necessary. Let's move on to variable length subnet masking. In this case, every network receives individual number of IP addresses, hence the name variable. Each network is considered and a suitable subnet mask is calculated for it. Again, we can see the same example, and we can use this file to spare some time with the calculations. So again, we have the same network address, initial network address, and we have the same requirements, and we already calculated the number of hosts, and actually this is 172. Okay, so the first steps are quite similar. We need to write down the initial subnet mask, which is written down here. Check the required number of hosts in the power of 2 for each network, which is also done here. See if the given network has big enough address space, and yes, it is done here. We have enough address space, and calculate a new subnet mask based on the number of hosts of the biggest network. So again, the biggest network is 512, and the subnet mask for this will be /23 because we need 9 zeros to have 512 number of hosts, because 2 to the power of 9 is 512. And the magic number will again remain the same, so we can leave it as it is here. And again, I will delete until this line here. So again, the networks increase by 2 in the third octet, so we have these same networks but with 7 everywhere, just to not mix it up with the previous example. So as we can see here, both for the 500 number host and the 310 number host networks, we need to use 512 host networks, so these can remain the same as in the previous example. However, in case of the third network with 244 hosts, we should use a 256 host network. Otherwise we would waste the address space. So let's use the next available network which has not been used yet, which will be the network 172.10.4.0/23. Alright, as we know, this network can host 512 number of devices. But we need a network that can host only 256 number of devices. So we need to now calculate a new subnet mask for these networks. So we need to calculate how many zeros we need, and for this, if we raise 2 to the power of 8, it will be 256. So we need 8 number of zeros in the subnet mask. Okay, so write down this subnet mask here. Okay, I just copy this one, and actually this will be /24, a well-known subnet mask with hosts 256. Okay, now we should check the magic number here. The magic number, again, is the number with which every network increases. So, and it can be identified or found by looking at the first or the last one in the subnet mask, which is at position 0, and we can see for 0 it will be 1. So the magic number is 1. So now, using this network, we actually divided this network into two networks, and then that 4.0/23 will be our first network, and the magic number is 1, so it will increase by 1 only, /23. I am sorry, /24. And also we increase in the third octet because the last one is in the third octet. Okay, so now we have these two networks, but we need to use only one from these networks, so we reserve this network to the 244 host network. Moving on, for the 50 host network, for the 250 host network, we should use the network with subnet mask hosting 64 number of devices. Now we have 255 number of devices in this network, and we need to divide this into smaller parts hosting 64 number of devices. So let's see, 2 to the power of 6 is, I think, 64, but let's check this one. Yes, okay, sorry, it's late. And this means that, again, sorry, we need 6 zeros in the new subnet mask. Okay, so the new subnet mask will be not /24, but it will be //26 with hosts 64. 1, 2, 3, 4, 5, 6. Okay. Again, check the magic number in this network, which will be the position of the last one here is at, as we can see, at 64. So the magic number will be 64, which means that the networks increase by 64, and the last one is in the fourth, the last octet, so it will increase in the last octet. Okay, so write down these networks. So the initial network what we used was 172.10.5.0/24. Okay, and we increase it by 64 in the last octet. So this means that 172.10.5.64 and /26 is our first network. And sorry, 172.10.5.128/26 is our second network. And let's write down the third one real quick. (6.0/26). Alright. Now, we created again 2 new networks for these 2 50 host networks. So we can write down our solution here. 5.64. I am sorry. A 0 is missing here. It's because we can use also the 0 network here. So this will be 0/26, and this will be so now these 2 networks are out and are assigned to these 2 networks, and all is left is to assign network addresses for these 3 2-host networks. So for these we will use a subnet mask that hosts maximal 4 number of devices. So 2 to the power of 2 is 4, so we need 2 zeros in the subnet mask. So the subnet mask will look something like this, and it can host 4 and 2 usable devices. Okay, and now we need to check the magic number again, and the magic number is the last one in the subnet mask and its position. So it is in position 33, which means that it will increase by 4. So the magic number is 4. And using this network 172.10.5 128/30 will be our first network. 172.10.5.132 will be our second network, and 36 will be our third network. This means that we have finished with the exercise and created network for all the required networks. We created addresses and used the least amount of IP addresses possible for each individual requirement. So this is how you configure variable length subnet masking. Another thing I would like to show you is the advantage of variable length subnet masking over fixed length subnet masking. For this, I wrote down another scenario with these requirements and using this initial network. And we are going to solve this in fixed length and variable length subnet masking. I wrote down the details of the exercise. Here you can see the initial network that we are given, and here are the requirements for each network. As you can see, I've already converted them to powers of 2 to better deal with them. Here is the subnet mask of the initial network, and as you can see, it has 11 zeros in it, which means that we have 2 to the power of 11, aka 2048 available IP addresses. As you may know, fixed length subnet masking means that we give the same subnet mask for each network, and always the highest requiring network is considered. In this case, this will be the 512 network, which means that each network here will get a subnet mask that can host 512 number of devices. From that, 510 is usable. So this means that each network will have a /23 subnet mask hosting 512 addresses. The address range therefore required for this exercise exceeds 2046. Therefore, we can say that it will not be enough. And using fixed length subnet masking, we could not come up with a solution for this exercise. Now let's see a solution for variable length subnet masking as well. In case of VLSM, we need to ask the same question: is it enough? Is the 2048 available IP address is enough? Let's see. For each network, we will have a variable length subnet mask according to the required number of devices. The address range will be the sum of these numbers here. So we have two 512 networks, one 128 network, and three 4-slot networks, which add up to 1164. So yes, we can say we have enough addresses because we do not exceed 2048. Moving forward, we can see that the highest number of required devices is 512, and therefore in the new subnet mask we will need 9 zeros, because 2 to the power of 9 is 512. So we will have the new subnet mask /23 with 9 zeros, and we need to find the magic number, the number with every network increases with. We can see that the last one in this subnet mask is in the 3rd octet and in the 2's position. So therefore the magic number will be 2. And this way we can write down the newly created networks. And you can see that I have already reserved these 2 networks for the 2 512 host networks. I wrote them down here. And we can go on with the next network in this list, which is the 16.20.4.0/23 network. And we will use this for the remaining 4 networks. For the next network, we need 128 number of hosts, So this means that 2 to the power of 7 is 128, so we need 7 zeros in the new subnet mask. So from this subnet mask, create this subnet mask with 7 zeros, and we need to find again the magic number, which will be the last one's position, which is this one. So the magic number will be 128. So using this 16.20.4.0/23 network, we can create a new network that fits 128 number of devices, effectively 126. So we can write down here 16.20.4.0/25. Alright, so we use this network, and we can go on with this second network here and use this as our initial network for the 3 2-host networks. For the 3 2-usable host networks, we need a network that fits 4 addresses in its network. This means that 2 to the power of 2 is 4, so we need 2 zeros in the new subnet mask. Therefore, the new subnet mask will be /30 with 2 zeros, and the magic number is given by the last one here, which is in the 3rd position in the last octet, and in the 3rd position it is 4. So the magic number will be 4. So using this initial network, we can divide it into 3 smaller networks, and you can see that indeed the number with which every network increases is 4. Alright, so I can write down here these 3 networks, and we are ready with this exercise. We can see that with variable length subnet masking, we could manage to fit the requirements in this initial network here. Although with fixed length subnet masking it was not possible. Therefore, we always use VLSM over FLSM to preserve IP addresses.